This is the sixth part of the course Probability and Stochastic Processes, in which we are going to talk about deviation. We are going to talk about how a random variable deviates from its mean or its average. A random variable may have values that are close or far away from its mean or expectation. We would like to have some way of measuring the performance of a random variable compared to its expectation. One way to do this is by using the variance. The variance VR of a random variable R is defined as follows. The variance is equal to the expectation of R minus ER squared. This means that the variance is the expectation of the squared difference between the values of a random variable with its expectation. If we interpret the expectation as the average, then the variance is simply the average of the squared difference between the values of a random variable and its average. So we are performing averaging twice right now. Note that in variance we use square. Squaring here avoids cancellation, otherwise R minus ER may be positive, may be negative, and they may cancel each other. Squaring basically avoids this. We can of course perform this by using absolute values, but then squaring has better properties than just absolute values. Let's take an example. Assume that we have two games. A, in which if we win, we get $2 with probability 2/3, and losing $1 with probability 1/3. And B, we get $1,002 with probability 2/3 if winning, and losing $2,001 with probability 1/3. These two games are strikingly different. We see that the money involved are really different. Let's try to find out the expectation of these two games. The expectation in the term of payoff. The expectation of game A is equal to the winning, namely $2, multiplied by the probability 2/3 plus the lose, namely minus $1, multiplied by the probability 1/3. So the average payoff therefore is equal to 1. So that means that we expect that we will get $1 in every game. Game B, on the other hand, the expectation of game B is equal to $1,002 multiplied by $1,002 multiplied by 2/3 plus minus $2,001 multiplied by 1/3, which is also equal to 1. We see that the expectation of these two games are equal, namely 1. We expect that we will get $1 every game. But you get the feeling that game B is a little bit more riskier, more dangerous, because if you lose in one game, then you will lose $2,000. We can actually see this and quantify this by looking at the variance. Let's look at the variance of game A. If you look at the definition of the variance of A will be equal to the expectation of E minus EA squared. So let's take let's take A minus EA first. So A is the number, the value of the random variable minus EA minus its expectation. So the value first is equal to 2 minus 1. So this is equal to 1 with probability 2/3. And the other one is minus 1, namely if we lose, minus, yeah, minus EA, and this time is minus 1, so this is minus 2 with probability 1/3. And we can square this, so the square will be 1 with probability 2/3 and 4 with probability 1/3. So that means the variance will be the expectation of this, namely weighted by the probability. 1 here weighted by 2/3 and 4 here weighted by 1/3. The final result is 2. So the variance is equal to 2. On the other hand, the variance of B can be also computed similarly. So B equals B minus the expectation of B. So the value of B if we wins is equal to 1002 minus 1. So this is 1001 with probability 2/3. And on the other hand is minus 2001, yeah, minus 1, so minus 2002 with probability 1/3. And you can square this, resulting in 1,002,001 with probability 2/3 and 4,008,004 with probability 1/3. And you can then compute the expectation of the square, namely 1,002,001 multiplied by probability 2/3 plus 4,008,004 with probability 1/3, and the resulting variance is 2,004,002. This variance is way larger than the variance of A. This variance basically tells us about how it deviates. The payoff of game A is close to its expected value, namely $1. The payoff of game B is far away from its expected value, and this high variance indicates high risk. Notice that the unit of variance is not on par with expectation, because a variance, basically in the variance we perform a squaring. That means that if the value of a random variable is of a particular unit, then the variance will be the square of that particular unit. Now we can make them on par with each other by the following definition: the standard deviation. The standard deviation sigma out of a random variable is simply the square root of the variance of that particular random variable. So the standard deviation is therefore also called the root mean square. For example, the standard deviation of game A is equal to the square root of 2, it's around 1.41, and the square root of B, and the standard deviation of B is equal to the square root of 2,004,002, which is around 1,416. And you see, this is closer to the value of the random variable itself. You see the we get a random variable. If you see here the random variable, the B wins 1002 with probability 2/3 and losing 2001 with probability 1/3. So this is on par with the value of this variance. And this provides us with a closer meaning of this variation, of this deviation. Okay, now of course we can use that definition of variance to calculate variance. But actually, There is another way to formulate the variance by using the linearity of expectation, and this is described by the following theorem. For any random variable r, the variance r is equal to the expectation of r squared minus the expectation of r squared. How do we get this? This is actually easy to prove from the previous definition. The definition basically says that this is equal to the expectation of of r minus the expectation of r squared. So if you take the square, then this will be the expectation of, yeah, you take the square, r squared minus 2r multiplied by er plus er squared, and this is the expectation of this one. So then this will be the expectation of r squared minus 2. Look at this, the expectation of r, and the expectation of r is simply the expectation of r. So this will be 2 expectation of r squared, yeah, plus the expectation of r squared. So the final result is the expectation of r squared minus the squared of the expectation of r. For example, this allows us basically to compute the previous expectation easily. If we have known the expectation of a, the expectation of a is equal to 1, then the expectation of a squared, just take this, for example, just take these 2 and square them. So that means this is 4. The expectation of a squared, this one, take this and square them, which is equal to 1. So the final result is 3. Therefore, the variance of r, the expectation of a squared, namely this one, which is equal to 3, minus the expectation of a squared, namely this one squared, which is equal to 2. And this allows us easy computation. The other thing is that notice that a variance is a positive, is a non-negative value. A variance can never be negative. Because what? Because this is the expectation of a squared. So the squared can only be 0, cannot be a negative value. So that means the variance is larger or equal to 0. A consequence of this is expressed in the following corollary, namely for any random variables r, the expectation of r squared must be more or equal to the expectation of r squared. Let's take a look at several important properties of the variance. The first one is related to the indicator random variable. If I is an indicator random variable and the probability that I is equal to 1 is equal to p, so the probability is equal to p, then the variance of this indicator random variable is equal to p minus p squared is equal to p multiplied by 1 minus p. If Rn is a random variable with uniform distribution, with a sample space S from value 1 until n, then the variance of this random variable is equal to n squared minus 1 divided by 2. And the last one is that for any random variable r and constants a and b, real constants n and b, then the variance of ar plus b is equal to a squared multiplied by the variance of r. Notice that b here simply disappears and a becomes a square, because of course a variance is something squaring the random variables. And if we take this, if this is a variance, then on the level of standard deviation, the standard deviation of AR plus B is equal to the absolute value of A multiplied by the standard deviation of R. Why is it the standard deviation is the absolute value of A? Because this is the square root, yeah, the square root of A squared. The square root of A squared, no matter what A is the absolute value of A. Another important property is the summation. The following theorem says that if R1 and R2 are independent random variables, look at the condition that they must be independent, then the variance of R1 plus R2 is equal to the variance of R1 plus the variance of R2. Namely, that means that if the two random variables are independent, then the variance of the sum equal to the sum of the variance. If you remember, when we are talking about expectation is linear. Namely, we need no condition whatsoever in expectation. The expectation of the summation of two random variables is simply the summation of the expectation of each random variable without condition. But in variance, you need the condition that they are independent. What if we have more than just two random variables? Then the condition, the necessary condition, is that they are pairwise independent. We don't need actually for them to be mutually independent. Pairwise independence is enough. If R1, R2 until Rn are pairwise independent random variables, then the variance of the summation of I is equal to 1 until n Ri is equal to the summation of I is equal to 1 until n, the variance of Ri. What about the product rule? We don't have any product rule for variance, and of course we don't have also division rule for variance. There is no product rule for variance, even with mutual independence, for example. Then we can use this to compute, to look at our mean time to failure that we have seen from the previous lecture. Let random variable C express the number of time steps until a crash occurs if a crash occurs in every time step with probability P. So we have here a time step, the first time step, the second time step, and so forth. And in every time step, we fail with probability P. We have already seen that the mean time to failure, namely the expectation of this random variable C, is equal to 1 divided by P. What we want to know right now is the variance. For this purpose, we will compute the expectation of C squared. How do we compute this? One of the simpler way of computing this is just taking the square, and there are two possibilities. The first possibility is that the failure occurs in the first time step, and this happens with probability P, or the failure occurs in other time steps, and this happens with probability 1 minus P. Yeah, so this one here, if you think about it, the payoff is 1 squared, and happens here outside of 1, outside of the first time step, is actually expressed. Look at this. So the expectation of this, the average of this one, is equal to the expectation of C plus 1 squared. Yeah, and by rearranging these, basically we will obtain that the E c squared, the expectation of c squared, will be equal to 2 minus p divided by p squared. Therefore, the variance is equal to E expectation of c squared minus the expectation of c squared, namely 2 minus p divided by p squared minus 1 divided by p squared. The final result is 1 minus p divided by p squared. Binomial distribution. Let's look at the variance of binomial distribution. If random variable j has a binomial distribution with parameters n and p, then the variance of this random variable j is equal to n minus p, n multiplied by p, n times p times 1 minus p. How do we get this? This is actually quite simple. This random variable j can be considered as the sum of n indicator random variables ji from j1, j2 until jn, in which ji is an indicator random variable, so it can only have values 1 or 0. 1 happens when the random variable, when the ith tossing of the coin, for example, produces a head, and 0 otherwise. So that, therefore, we can consider that this j is consider that this j is the number of heads that we have that is produced by tossing and by performing and tossing of coins with probability, for bias coin with probability p. Okay, therefore the variance of gi, yeah, because this is the, well, this is basically this returns here to the variance of the indicator random variables. For every indicator random variables, then the variance is equal to p multiplied by 1 minus p. So therefore, the variance of gi is equal to p multiplied by 1 minus p, and the variance of j is, therefore, we just have to sum them up. This is, of course, by this can only be done if these indicator random variables are at least pairwise independent of each other, which is they are, because one tossing of a coin does not influence by another tossings. So the variance of j is equal to the sum of I is equal to 1 until n, the variance of ji. Each one of them has the variance p multiplied by 1 minus p. So this is n time, and we have n times p times 1 minus p. Okay. Now, variance gives a rough idea of how much a random variable deviates from its mean. So we get the idea of this deviation. So how much a random variable is off from its mean when you perform a particular experiment, for example. But it does not give specific bounds on the probability of the deviation exceeding a certain threshold. You may want to know this probability, the specific bound on this probability. For example, let's take this example. IQ, intelligence quotient, is defined in such a way that it always has a mean of 100. So that basically means that the average IQ is equal to 100. So we define it in this way. The average of IQ of everyone in the population is always equal to 100. If this is the only information that we have, we can actually already infer that at most 1/3 of the population can have an IQ of 300 or more. Why? Well, if you look at this, assume that we have IQ and the average of the IQ is equal to 100. Yeah? If there are more than 1/3 of the population having IQ of 300, if there are more than 1/3, if there are more than 1/3 of the population having IQ 300, then the other 2/3 will not be able to offset this 1/3 to obtain the average 100. Yeah, so the other 2/3 will not be able to offset it. So even though the other 2/3 we set them to 0, for example, you can set them to 0, have IQ with 0. The other 2/3 will basically have IQ of 0. Yeah, that's the only thing that we can, because otherwise it is, of course, it cannot be negative. It can be only with 0. Yeah. So therefore, this 1/3 of the population, yeah, the maximum IQ that they have is equal to 300. So that means at most 1/3 can never be more than 1/3 of the population can have IQ of 300 or more. And this is what is expressed by the Markov's theorem. If R is a non-negative, look at this, is a non-negative random variable, because if it has a negative, of course, this is a different way altogether. Yeah? If it's a non-negative random variable, then for all x larger than 0, the probability of R more or equal to x must be less or equal to the expectation of R divided by x. So previously, if we ask the probability that the IQ is more or equal to 300 must be equal to the expectation, namely 1, yeah, 100 divided by x 300, namely 1/3. Let's look at the corollary. If R is a non-negative random variable, and for all C larger than 1, it must be larger than 1, it cannot be smaller than 1, the probability that R has a value more or equal to C multiplied by the expectation of R must be less or equal to 1 divided by C. Look at this, this is a polynomial. And this bound is actually the best that we can do based on only this knowledge of the expectation. And this is actually the best in the sense that without any condition whatsoever, including independence. For example, let's ask ourselves, if we flip 100 fair coins, what is the probability of getting all heads? If we use this Markov's theorem, then this probability must be less or equal to 1/2. Yeah, must be equal to 1/2. Cannot be more than, less or equal to 1/2. Cannot be more than 1/2. And you may think that this is a big bound, or we cannot say anything, but it's actually a very good bound in the sense that it does not take into consideration any independence whatsoever. These 100 fair coins may be dependent of each other. The large dependence may be they have the same result. But even though they have the same result, they can only be 1/2. Yeah, either head or tail for all of them. Okay. Now in Markov's theorem, pay attention that R must be non-negative. What if R can be a negative value. In this case, you can shift the random variable. And the way to shift this, for example, by using these two theorems. And these two theorems is actually also can be used for bounded variables. If R is a random variable and R is larger or equal to a lower bound, so that's why you can shift the random variable. That's one way to shift the random variable. You can define a new random variable that's shifting the original random variable. And the value of R is larger or equal to L for some L, then for all x larger than L, the probability of R larger or equal to x is less or equal to the expectation of R minus L divided by x minus L. This is the lower bound. And similarly for the upper bound, if U is a real number and R is a variable, random variable such that R is less or equal to U, so U is the upper bound of this random variable, then for all x less than U, the probability of R larger or equal to x must be smaller than equal to U minus the expectation of R divided by U minus x. For example, suppose that we know the class average on a midterm is 75 out of 100. You know only this information. And then you ask yourself, what fraction of the class scores below 50, for example? Then the previous theorem basically allows us to compute this, namely the probability of R is larger or equal to 50 is equal to less or equal to 100 minus 75 divided by 100 minus 50, namely 1/2. That means that at most half of the class scores 50 or worse. If you pay attention, actually in using this theorem, we just use this theorem about a random variable to conclude facts about non-random data. How is it possible? Look at this. The probability that the random variable R has value less, more or equal to 50 is actually the same as the sum of all SI. SI is the score, yeah, the possible score is less or equal to 50, the probability that R is equal to SI. What is this probability? This probability basically means that the probability that a particular student has a particular score. And how do we get this probability? We get this probability, of course, by using frequency. We calculate, we compute, we find out the number of students with score SI, and we divide this by the number of students. So you see, in the end, this probability can be translated into something non-random. And this is equal to 1n multiplied by the number of students with score 50 or less. Chebyshev's theorem. For any random variable, we have the following lemma, namely that we can basically generalize the previous Markov's theorem by taking the power of the random variable and the power of x, any power whatsoever. So this lemma basically tells us about this. For any random variable R, alpha elements a positive real number and x more than 0, the probability that the absolute value of R has larger or equal to x must be less or equal to the expectation of R, the absolute of R to the power of alpha divided by x to the power of alpha. And alpha can be anything. Now, a specific case is when alpha is equal to 2. In this case, we are dealing with Chebyshev's theorem. If R is a random variable, look at this. There is no condition right now. It does not have to be positive or non-negative random variable, and x is a positive real number, then the probability that the absolute of R minus the expectation of R. What is this? This is actually, the R minus the expectation of R is larger or equal to X is less than equal to the variance of R divided by X squared. So right now, if we know two things, so if our knowledge is greater, namely we know the expectation and we know the variance of the random variable, then we have a more tight bound. And we can also actually see this. If R is a random variable and C is a positive real number, then the probability that R minus the expectation of R has value is larger or equal to C multiplied by the standard deviation of R, then this probability must be smaller or equal to 1 divided by C squared. Look at this. So this is right now exponential. So previously we have 1 divided by C when we are dealing with Markov's theorem. So right now our bound is 1 divided by C squared. So this is a much tighter bound. Let's see an example. Suppose that the standard deviation of IQ is 10. Suppose that we are given this information and we know that IQ has the average has a mean 100. How rare is an IQ of 300 or more? If the only thing that we know is basically the average of the IQ, we have already seen previously that the probability that someone has IQ of more or equal to 300 is less or equal to 1/3. But what if we know right now also the standard deviation? Yeah, so equal to 1/3. So the Chebyshev basically tells us that the probability that R is more or equal to 300 must be less or equal to the probability that R minus 100 is larger or equal to 20 multiplied by this one. Look at this. Standard deviation is equal to 10, so this is 200. And this must be smaller or equal to 1/400. This is much, much smaller than the bounds provided by the Markov's theorem. So knowing the expectation and the variance of random variables allows us to bound this probability tighter. So the probability that a random variable strays by more than n standard deviations is no more than 1 divided by sigma squared. And if the PDF of this random variable has a bell curve shape, the width of this bell, this is basically what we mean by straying by more than the standard deviation. The width of the bell must be on par with sigma, namely is O sigma. This is the end of the 6th topic in the course of probability and stochastic processes. Thank you.